Bismillahirrahmanirrahim. Numerical problems, Unit 11, Electrostatics. This is Physics 12 KPK. Problem 1. To find the magnitude of force of attraction between an iron nucleus and the innermost electron. Iron nucleus positively charged, innermost electron is negatively charged, there will be force of attraction. The data is given, iron nucleus is 26 protons, E represents the proton here. Distance R is equal to 1 into 10 power minus 12 meter, and the charge on a proton or an electron is equal to 1.6 into 10 power minus 19 coulombs, and the value of K that you all know to find the magnitude of force F. Now the formula that we use is the electrostatic force equal to K Q1 Q2 over R square. To total charge in the nucleus in terms of coulombs is calculated as Q1 is equal to 26E into 26 into 1.6 into 10 power minus 19. Calculating it results in 4.16 into 10 power minus 18 coulombs. Now force is 9 into, this is the value of K, putting in these values of nucleus charge, and this is the charge on an electron, and this is the distance, results in approximately 6 into 10 power minus 3 Newton. The problem 2 has been done separately. 3 different methods have been explained and thoroughly, and that includes the shortest and the easiest method too. And the link to the problem 2 is given below. Problem 3. Two equal and opposite charges of magnitude 2 into 10 power minus 7 coulombs are placed 15 centimeter apart. Find the magnitude and the direction of electric intensity at a point midway between the charges, and what force would act on a proton at that point. Now QA, QB and the distance. This is shown here. This is QA, this is QB. And since the electric field intensity is to be found at the midpoint is divided into 2 equal halves. That means the distance from A to M is R, and from M to B is again R. This is half of this distance, which is 0.075 meter. To find the electric field intensity E at midpoint, electric field intensity's formula is equal to KQ over R square with the direction vector R. Total electric field intensity at any point due to 2 opposite charges is the sum of the intensities due to both the charges. That means if we need to find the total electric field intensity at this point, it is the electric field due to charge A that will be away from the charge, positive charge, and it will be toward the negative charge. This is electric field intensity due to charge B. The total electric field intensity at this point would be EA plus EB. Similarly, it will be again due to charge A, it will be away, due to charge B, it will be toward, and the total will be in the same direction. The total will be sum of EA and EB. Now we need to find it at midpoint A, so we put it at the midpoint, and E is equal to EA plus EB is our total electric field intensity. Now electric field intensity, we use this formula again here, and it is KQA over R square plus KQB over R square. I am only taking the magnitudes here. Vector I will put later in the answer. Since QA and QB are both same in magnitude, we put it as Q. So E is equal to KQ over R square plus KQ over R square. Since these are the same quantities, we use it as E is equal to 2KQ over R square. Now put in the values, and that results in 640,000 Newton per coulomb. Putting it into the answer, the book answer, that is 0.64 into 10 power minus 6 newtons per coulomb, and this is the direction vector. Direction is from A to B. Now to calculate the force on a proton At this point, midpoint, that is F is equal to QE when Q is equal to 1.6 into 10 power minus 19 coulomb. Since electric field intensity is 0.61 into 10 power minus 6, we multiply it with the charge on the proton, that is Q, and 1.6 into 10 power minus 19, and that results in 1.024 into 10 power minus 13 Newton. Problem 4. Two positive point charges of 15 into 10 power minus 10 coulombs and 13 into 10 power minus 10 coulombs are placed 12 cm apart. Find the work done in bringing two charges 4 cm closer. These are the two charges, Q1 15 into 10 power minus 10, Q2 is 13 into 10 power minus 10, and distance is 12 cm, which can be written as 0.12 meter, and this is the point P. Point A is 0.12 meter apart, and this is the point B. And now this is the formula. Work is done from A to B, 4 cm. The formula that we use is work from A to B is K Q1 Q2 bracket 1 over RB minus 1 over RA. Now delta R is equal to 4 cm. We need to find what is RB from point P. So for that, delta R is equal to RA minus RB. It is from RA to RB, delta R. So RB is equal to RA minus delta R. Now putting in the values 12 cm minus 4 cm results in 8 cm, which is equal to 0.08 meter. And this we are representing here. From P to this point B is 0.8. Now substituting these values into this formula results in, this is the value of K, this is charge 1, this is charge 2, and I have colored it to make it simpler for you. Calculating these colored values, green colored values, return in this, and calculating this bracket is equal to 25 over 6. Now further calculating results in 7.3125 into 10 power minus 8 joules. Problem 5. A hollow sphere is charged. A hollow sphere is charged to 14 microcoulomb. Find the potential at its surface, inside the sphere, and at a distance of 0.2 meter from the surface. The radius of the sphere is 0.3 meter. Now Q is the charge 14 microcoulomb inside the sphere. Radius is 0.3 meter. To find potential at surface, potential inside, and potential at a distance 0.2 meter away from the surface. The formula for the potential that we use is, for potential is work done per unit charge, which is equal to KQ over R. Now potential of surface. Potential at surface is the distance R will be equal to 0.3, which is the radius, and putting in these values in the formula, that result in 420,000 volts, which is equal to 42 into 10 power 4 volt. The potential inside the sphere. For potential inside the sphere, note that the electric field E inside the sphere is 0. Since potential is equal to E dot delta R and E is equal to 0, so delta R is equal to 0 dot delta V is equal to 0 dot delta R. That tells us that delta V is equal to 0. There is no change in, there is no difference in the potential. And since delta V is equal to V inside minus V on the surface, since this is 0, so V inside is equal to V on the surface, which will be equal to 42 into 10 power 4 volts. Now we need to calculate this point 0.2 meter away from the surface, and this makes the total distance from the center 0.3 plus 0.2, which is equal to 0.5 meter. Putting in these values results in 252,000, can be written as 25.2 into 10 power 4 volts. Now problem 6. If 280 joules of work is done in carrying a charge of 2 coulombs from a point where the potential is minus 12 volt to another point where potential is V, calculate the value of V. Since we are doing the work on the charge of 2 coulombs, that means we are taking it from a point of lower potential to the point of higher potential. So name the point at the lower potential as point A and the point at higher potential as point B. The given data is potential at lower point A, VA. This is the potential at lower point since we are carrying from here to a higher point, potential point. That VA is equal to minus 12 volt. Work done in moving the charge is from work done from A to B is 280 joules. Total charge moved Q is equal to 2 coulombs. To find the electric potential VB at point of higher potential B, the formula that we use is delta V is equal to VB minus VA is equal to work done from A to B divided by Q. Now, substituting these values, and for VB that we will use V that is given in the question, that is V minus 12 is equal to 280 over 2. This 2 is the charge and 280 is the work done in joules. Cutting these two values, this makes it 140 and this becomes V plus 12 is equal to 140. Moving 12 to the right side results in 128 volts. The electric potential of the other point is 128 volts. Problem 7. The electric field at a point due to point charge is 26 Newton per coulomb. Electric potential at this point is 13 joules. Calculate the distance of the point from the charge and the magnitude of charge. E is equal to 26 Newton per coulomb electric field. Potential difference between the 2 points within the electric field is delta V is equal to 13 joules per coulomb, which is volt. We can write it delta V is equal to 13 volt. Find the distance between the 2 points delta R within the electric field and the magnitude of charge. So delta R is to be found and the charge, magnitude of the charge is to be found. So to calculate the distance, use electric field is equal to delta V over delta R, or making delta R the subject, delta V over electric field E, putting in the values, so delta R is equal to 0.5 meter. Now to calculate the magnitude of charge, use E is equal to KQ over R square, putting in the, or making the Q as the subject now. When making the Q as the subject, this R square goes with E and K in the denominator. So Q is equal to R square E over K. Now putting in the values, that will result in Q is equal to 7.22 into 10 power minus 10 coulombs. Which can be written as Q is equal to 0.722 into 10 power minus 9 coulomb, which is 0.722 nanocoulombs. Problem 8. 2-point charges of 8 microcoulomb and minus 4 microcoulomb are separated by a distance of 10 centimeter in air. At what point on the line joining the 2 points, 2 charges, is the electric potential 0? So the formula that we use is V is equal to KQ over R, that is for the electric potential. Let us assume that the 2 potentials are 0 at a point P, distance x from charge Q2. And if this is distance x from charge x from charge Q2, since the total distance between Q1 and Q2 is 10 centimeter, the distance from P to charge Q1 will be 10 minus x. This is distance x. This will be 10 minus x, shown here in the figure. So that means potential due to charge 1 at point P will be 8 into 10 power minus 6k over 10 minus x, and potential V2 due to charge Q2 at this point P will be minus 4 into 10 power minus 6k over x. I have intentionally used the value k here and not using the value of k just to shorten it, and because it will not be used. Now, when there are 2 or more charges, then the net potential at any point is sum of the potentials due to each charge. That means V1 plus V2 is equal to V net. Like at point P, the total charge will be equal to V1 plus V2 is equal to V net. Now, since V net is equal to 0, V1 plus V2 is equal to 0. Now, sum of the two numbers can be 0 if and only if one of the number is positive and the other is negative. Remember, that's a mathematical concept. Positive charge has a positive potential and negative charge has a negative potential, meaning V2 is negative. So since we put in the values and we got this 8 into 10 power minus 6 and negative 4 into 10 power minus 6k, putting in these values and now moving this negative value to the right side, making it positive, and we note that k can be cut from with k here. 10 power minus 6 can be cut from 10 power minus 6. 4 is a factor of 8 and it can further reduce this 8 as well. So dividing both sides by 4 into 10 power minus 6k results in 2 over 0.1 minus x equal to 1 over x. Cross multiplying gives us 2x is equal to 0.1 minus x. This minus 1 minus x goes to the left hand side and is added here into the 2x. So moving x to the left hand and converting 0.1 as 1 over 10 makes it 3x is equal to 1 over 10. Now since it is 3x, so moving x dividing with x makes it x is equal to 1 over 30 meter. Converting it in centimeter makes it x is equal to 1 over 30 into 100, which is 3.33 centimeter. X is the distance from minus 4 microcoulomb charge, which is 3.33 centimeter, and now distance from 8 microcoulomb charge is given as 10 minus 33, which is equal to 6.67 centimeter. This is a rather a better calculation, and this sum of these two distances makes it equal to 10. Problem 9. An electron with an initial speed of 29 into 10 power 5 meter per second is fired in the same direction in a uniform electric field with a magnitude of 80 Newton per coulomb. How far does the electron travel before being brought to rest momentarily? So what is the direction of an electric field? The direction of electric field is always away from the positive source. And this is the positive source electric field, uniform electric field given here shown. Its strength is 80 Newton per coulomb. And now just see, there is an electron which is fired. If I place an electron in an electric field, the natural direction would be, it would go toward the positive source. But since it is stopping, that means it is going along the magnetic electric field, and this is the natural direction. And since it is fired, it is going in this direction, where it will stop at certain distance and then it will return back. So it is given situation, since it is stopping, it's fired in the same direction as that of field. We need to find the distance. S is usually used in physics for distance, but in this chapter we are using R for the distance or the delta R. This is the distance till it stops. One approach to do this is using since there is a change in the speed, there is an acceleration. So since there is an acceleration, we can use 2as is equal to v square minus vi square. That is the third equation of motion. And calculate the acceleration a using F is equal to ma. And we do not know the F either. So we can use mass of an electron as 9.11 into 10 power minus 31, and use for F we can use E is equal to F over Q. Charge on an electron, this Q is equal to 1.6 into 10 power minus 19 coulombs. So the other approach is using the law of conservation of energy, and this approach looks easy to me. I'll use this approach for law of conservation of energy. So the given data, Mass of an electron, charge on an electron, the kinetic energy of electron is half mv square. And since the electric field is F over Q, so since an electron stopped and lost its kinetic energy, then according to the law of conservation of energy, the loss in kinetic energy equals work done. That means F dot delta R, where delta R is the distance that it traveled before it stopped. So F dot delta R is equal to half mv square. Since F is equal to Q dot E from here, substituting, we get F is equal to QE, and Q dot E dot delta R is equal to half mv square, making delta R the subject, moving Q dot E to the right hand side, half mv square dot 1 over Q dot E. Substituting the values, all these values given here, we get in 0.299 meter, and that is the answer. Problem 10. Three capacitors of capacitances 4 microfarad, 6 microfarad and 8 microfarad shown here in the figure. 4 microfarad, this is 6 microfarad, this is 8 microfarad, connected in series to a 250 volt DC supply. Find total capacitance, charge on each capacitor, and PD, potential difference across each capacitor. The formula for the equivalent capacitor in series combination is given as 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Substituting the values, we get 1 over 4 plus 1 over 6 plus 1 over 8. The LCM is taken as 24. Now calculating these, 1 over C equivalent is equal to 13 over 24, and C equivalent is taking the reciprocal 24 over 13. This is the exact value, and approximating it 1.85 microfarad. Note that the net capacitance, this is very important to note for the conceptual point of view, for your MCQ sometimes, for your future tests in NET and other aptitude tests in universities. The net capacitance of a series circuit is less than even the smallest capacitor involved. Here, the smallest capacitor is 4 microfarad. The net capacitance is even less than that. This is a very important fact that you must keep it in mind. Okay, C equivalent that we calculated, I'm putting it here. 24 over 13 is the exact value, and 1.85. This is 24 over 13 microfarad is the exact value, and 1.85 microfarad is the approximate value. Now, in a series combination, the charge from the battery is stored on the extreme plates only. Remember, the battery will store charge on the extreme plates only. Charge cannot flow through the capacitors. Capacitors are open for the DC source. On the other internal plates and the other internal capacitors as well, like V2 here in this case, charge will be stored through induction, and it will be induced on the other plates as well as on the interior capacitors placed in the circuit. If one plate of capacitor is charged positive, the other will induce total amount of negative charge, and that plate will induce on the near plate positive charge, and the other plate has negative charge. Same thing will continue. Whatever number of capacitor is, they will all be charged with the same quantity of charge Q. The charge Q in a series circuit of capacitors is always same on all the capacitors. This means charge on each capacitor is same and is calculated as Q is equal to C equivalent V, because that we will calculate as C equivalent. And remember, C equivalent is always less than the smallest value of capacitors. If we put in a small capacitor, wherever it is placed inside the circuit, the charge will be placed according to that equivalent capacitance, and that will be less than the smallest value. So, placing in the values, I am using this 24 over 13 with this microfarad 10 power minus 6 into 250 volts. in order to get the exact possible value, the best possible value, and that is Q is equal to 461.5 into 10 power minus 6. That means 461.5 microcoulombs. That is 461.5 microcoulombs. Now again, these values we have calculated earlier. I am placing it here in case we need it for further use. Since Q is same on all the capacitors, the PD can be calculated using the formula Q is equal to CV or V is equal to Q over C. So V1 will be Q over C1, placing in the values 115.38 volts. This is V1 across this capacitor. Then V2 will be across this capacitor, that is Q over C2, 6 microfarad. Dividing it with 6 microfarad gives us 76.92. And similarly, V3 will be Q over C3 and 8 microfarad here, and that will give us 57.69 volts. Remember, adding all these voltages should result in the voltage of the battery, and that in this case gives us 249.99. Since we had been approximating these numbers, 249.99 is a very close number, and we consider it as correct. And this check I usually do for checking my answers. If it does not sum up to the battery voltage, that means there is some error in my working. So problem number 11, and it says find the charge on 5 microfarad capacitor in the circuit. This is a circuit given in this problem, and this is a 5 microfarad capacitor. We need to find the total charge on this capacitor. So that means to Q5, I rename this charge as Q5 is equal to C5 into V. That means I need to find the voltage across this capacitor. The voltage across this capacitor will be same as at this voltage across these 2 points, this point and this point. That means it will be same voltage for the 2 microfarad capacitor as well. So it is shown here. We call it VP because of this parallel combination, and voltage of the parallel combination will be VP. And in order to find this voltage, total voltage of the circuit is 6 volt. Once it operates in the circuit, there will be some voltage which will drop here, and the remaining will be here, and the sum of this voltage at 3 microfarad and the voltage at these both of these parallel capacitors is equal to 6 volt. Keeping this concept in mind, we need to find how much voltage drops here. That means V3 is equal to Q over C. And in order to find this V3 Q over C, what we need to know is the total charge Q passing through this place. Now, for that, in order to find the charge Q, we need to find the equivalent capacitance. Equivalent capacitance of all these 3 capacitors used here. And that is V is equal to Q over C equivalent. And in order to find C equivalent, what we do is first of all we will solve these 2 parallel capacitors and find what the total capacitance of these equivalent capacitance of these 2 parallel combination is. That means parallel combination is C2 plus C5. We are placing these values 2 microfarad, 5 microfarad results in 7, and this is 7 microfarad. Now these 2 parallel capacitors will be replaced with this one capacitor of 7 microfarad, this 2 and 5. Now these 2 are now placed in series. So to find the equivalent capacitance for the 2 capacitors in series using the formula 1 over C equivalent is equal to 1 over C1 plus 1 over C2. I would suggest not to put this formula here in the main body of the question. Such working should be done on the sideline, and the result should be placed in this. This makes the work of an examiner easy, and you make him happy. Otherwise, this working should be done, but do it on the sideline always. So this here gives us C equivalent is equal to C1, C2 taking the LCM C1 plus C2 and take a reciprocal on both sides gives us C equivalent is equal to C1 C2 over C1 plus C2. These are the two capacitors, and for two capacitors note that this formula is product over sum. Numerator is product, denominator is sum. And whenever you are doing it for two capacitors in series and two resistors in parallel, always use this formula, product over sum. This is very handy formula, particularly once you are solving the MCQs or you are doing some aptitude tests. You do not have to show all these steps in there. You have to solve it quickly, and product over sum formula solves it very quickly. So we are using this formula here, and the values given as 3 and 7. So 3 into 7 divided by 3 plus 7 results in 21 over 10, which is equal to 2.1 microfarad. And I have made this equivalent circuit. This is the equivalent circuit for this whole circuit of two parallel and one series to know the equivalent capacitance. It is 2.1 microfarad. So in order to calculate the total charge Q passing through this, that is equal to C equivalent V. So C equivalent is equal to 2.1 into 10 power minus 6 and times 6 volt. This gives us 12.6 into 10 power minus 6 coulombs. This is the total charge passing through the circuit. Now, since V3, this is the potential drop at the 3 microfarad capacitor V3, which is equal to Q over C. And this is the charge that we calculated, 12.6 into 10 power minus 6 divided by this 3 microfarad. Because we are calculating voltage drop at 3 microfarad, this is the C capacitance of the 3 microfarad, and this is the total charge passing through it, 12.6. So this gives us 4.2 volts, and since we know that potential at this point and potential at 3 microfarad capacitor both make it 6 volt, so calculating for the VP, we put in the values, and 6 minus 4.2 gives us VP is equal to 1.8. That means potential difference across these two capacitors which are placed in parallel is equal to 1.8 volts. So to calculate Q5, we will be needing this potential difference of 1.8 volts. Putting in these values result in 9 into 10 power minus 6, which is 9 microcoulombs. So the answer to this problem 11 is 9 coulombs. Now comes the last problem, number 12. If a 6 microfarad capacitor is charged to a potential difference of 120 volt and then connected to an uncharged 4 microfarad capacitor, calculate the PD across the capacitor. So given is C1 is equal to 6 microfarad, voltage is equal to 120 volt, C2 is equal to 4 microfarad. Now using Q is equal to C1V, we know that Q is equal to 6 into 10 power minus 6 multiplied by 120 volt. It gives us Q is equal to 720 into 10 power minus 6 coulombs. Now equivalent capacitance of a parallel combination. This is how we will be using it, because we then connected it with a 4 microfarad capacitor, and this is how we connected it. And we need to find the potential difference across these two capacitors, which are connected like this. Now, total capacitance of this circuit is equal to C1 plus C2 since they are in parallel, and that makes it 6 plus 4 microfarads, that means 10 microfarad. And now PD across the capacitors can be calculated as V is equal to Q over C equivalent. Since Q is equal to 720 into 10 power minus 6, C equivalent is 10 into 10 power minus 6, that results in 72 volts potential difference across these two capacitors. That is all from here. Do subscribe the channel so that you can get the necessary videos as soon as they are uploaded, and moreover, you need to learn the quick mental math techniques for your aptitude test after your exams. So better remain alert. Whenever I upload the mental math techniques, they will be available to you only if you subscribe to the channel. Thank you very much.